we'll go to current slide. I thought we'd go, there we go. Before we get going on this, the one announcement I made last week I'll continue making for a little bit anyway. As far as I know, they've still got the first mini-term student course evaluations open. I don't know how long they'll keep them open, if they're even still open, but they usually do keep them open a little while after the term's over. But don't wait, okay? If you or someone else you know is taking a mini-term course, please, you and encourage them to get the student course evaluations done. They are valuable to us. It lets me know how I'm doing as an instructor. It helps me know how to evaluate the instructors underneath me. And, you know, it's overall good feedback for the college and for us individually as well. All right, any questions on anything we've done so far? I guess I wanted to add this too. I think I told you last week that result of my doctor's appointment last Tuesday found out I was pretty severely anemic. I went by after a dermatology appointment, after a dermatology appointment on Friday to get the results of my labs because they hadn't come in by the time I left on Tuesday. I found out also my immune system is pretty low. So the immunoglobulins, IgG, IgM, and Ig something else, IgA or something like that. It's a grocery chain thing, but some sort of another Ig. All three of them were really low, and they said, you better watch for infections. So with this coronavirus thing coming up, it could be, things could get testy fairly quickly. So we hope they won't, but they could. All right. Any questions on anything we've done so far?
Have you graded my test?
I thought so. Let's see. Oh, I probably haven't put the grade on Blackboard yet.
Yeah, I haven't seen them on there.
So you probably don't want to publish it over YouTube, but
You can publish that.
okay. So kind of you to be so willing. Okay. We had already done example 5. Any other questions?
Wait, where are we? 12.5?
12.4. Almost to 12.5. We're going to be in 12.5 very shortly. But we're example. I was going to say we've already done example 5 where the screen is, but this is the last slide in the section. So we're on example 7. I probably should have gone to 12.5 and picked a slide there, but I just went where we left off and sort of dumb. We had just started. Well, any questions? Any other questions? Okay. We had started example 7. Since we hadn't gotten that far, let's just remind ourselves. Here's the position vector for a projectile. And they have the projectile over there, the path as your figure 1227. Here's the R of t is equal to 50 root 2 t in the I direction, and here's Fred. Okay. Plus 50 root 2 t minus 16t squared in the j direction. Okay? It says find the tangent components of acceleration when t is equal to 0, 1, and 25 root 2 over 16, which is one of my favorite numbers of all time. Okay? So what are a few of the steps you've got to do? Take a derivative, which is r prime of t, which also gives you, Ryan, okay? All right, so we got 3/5 of the folks here. Just missing Dawson and Josh. Hopefully they'll make it. R prime of t is also another name for v of t, velocity vector of t. And what would that be? 50 root 2 I, that's yes in Navy speak, plus 50 root 2 minus 32. I can't write. It's supposed to be a 2 and it was coming out of 6. Okay. 32 TJ. Okay. Hold on, put this in parentheses too since they did the earlier one, though it's not necessary. All right, that gives you your velocity vector. Okay? Anything else you might need? Magnitude of velocity vector, which we'll just call magnitude of v. I'm just going to leave off the of t. This is also going to be the speed, and what would that be? Anybody? At least a piece of it. Get me started on it. Okay, 50 root 2 squared. I'll write it down then. And then since we did that, what would be the next piece? 50 root 2 minus 32t, also squared. Okay? Especially for the second part, that makes a lot of sense. For the first part, what would that give you? Well, it's 2,500 times 2, which would be 5,000. Okay? Now, when you're squaring that second part, that's a binomial, so you square the first, which is another 5,000, right? Same thing. Minus twice the product squared, right? Well, twice 50 is 100, so that would be 3,200 root 2 t. If my quick calculations are right. And then what is 32 squared? One of those powers of 10. 1,024 t squared. Okay. We can simplify just a bit. This would be the square root of 1,000 or 10,000 minus 3,200. I can't write. Root 2 t plus 1024 t squared. Okay. Now, of all that mess, if I've done it right, this is one of those big multiples of 2. So remember, it came from 16, actually 32. 32 is 2 to the 5th. And then we squared that, that gave us 2 to the 10th, I believe. If that's right. Okay, so that's 2 to the 10th. Okay, this is 2 to the 5th times 4 times 5 for this part. So 2 to the 5th and 2 more 2's, that's 2 to the 7th. And this is 2 to the 4th and another 2 to the 4th. So this is at least got 2 to the, 2 squared, I'm sorry, 2 squared. 2 squared and another 2 squared. So that's at least 2 to the 4th here. So I know we can take out a 2 to the 4th out of the radical, right? And that would be 2 squared. So I know I'm not taking nearly enough out. Two to the 4th, 2 to the 4th, and take the square root of that. That's just 4. Surely we could take more out of that, but let's do 4 to begin with. Huh? Yeah. And yeah, and then we're taking 4. Yeah. Square root of 16 is 4. Yeah. So let's see, we might be able to get more. Let's do it. Let's take a 4 out of that. Well, 4 will go into 100. Well, two to the 4th out of this is going to be 5 squared, I believe. I think that's what's left. 25. I believe that's right. Okay, maybe so. Okay. Okay. 16 into 10,000. So we're taking 16 out. Okay, we're factoring out a 16 out of every term there, because the square root of 16 is 4, right? Okay, so 10,000 divided by 16 is 625. Okay, minus, and 16 into this would be 200 root 2t, if I did that right in my head. And 16 into that would 64 t squared. Okay. Now, 625 is all factors of 5, I think. And 64 has no factors of 5, so I don't think we can go any further with that. And for some reason, they left a factor of 4 in everything, and maybe that's going to help them somewhere, but I don't know why it should. But anyway, we'll leave it there. There's the magnitude of V. What else might we want to do? Go back up to the first derivative, which is the velocity. What else might we do? Help me, somebody. What are we looking for? Yeah. So wouldn't it be nice to know the acceleration? Okay, let's do that. What would that be? That's r double prime of t, which is v prime of t, which is negative 32J. Okay. Oh, I forgot. That's your acceleration. I needed to write one more thing down there. I didn't do it. That's your acceleration. Okay. Now, all they're asking for is the tangential component of the acceleration at 3 different times. So if we go back to the theorem 12.5, top of the previous page, 850, you'll see a fairly simple calculation for the tangential component of the acceleration. With, okay, one, you might not think is all that simple, is take the derivative of your magnitude of your velocity, which is what we just did. I think I'd rather not, if possible, okay? I think, and the A dot T, we got the A, but we don't have the T, and I'd rather not go with the unit tangent vector either, if we can get away with it. So, but the next one is V dot A, that's not going to be too bad, divided by magnitude of V, which is we got here. So let's do that one. This is A sub T. I don't have a lot of room for it. I'm going to erase some of my scratch here so I'll have a little more room. Okay? So, A sub T, the acceleration in the direction of the unit tangent vector. Okay? Its definition is V dot A divided by magnitude of V. And that's not a hard thing to do, isn't it? What is the dot product between this vector, the V vector, and the acceleration vector? That's not really too bad, is it? Because this doesn't have an I component down here. There's only the J component, so this would be this times 0. I can do that. That's 0. So this times that. That looks to be, I'll do it down here so it'll be easier to read. V dot A is, get out of there, okay? Negative 32 times this component here, which is 50 root 2 minus 32t. Right? Okay. So, and we're going to divide it by the magnitude of V, which is that mess down there, which I just as soon put off as long as possible. Okay. So this will be minus 32 times 50, I think, is 1600 root 2. Yeah, negative 1600 root 2 plus, and 32 squared we did already, that was our 1024, wasn't it? Okay, 1024 T. Okay. Now, and that thing we're going to divide by this thing. Okay. Now, before I do that, let me again factor out what we can. And this, the minus 1600 is going to be a minus 4 times another minus 4. So that's going, yeah, well, okay. A minus 16 times 100, right? Okay. Yuck, I just don't have enough room to write. I think I'm going to do it up here, if I can. let's factor as much of that as I can. This will be minus 16 times another, so I think that's going to be a minus 64 times 25 root 2. See if I did that right. 64 times 25, I hope, is 1600. Is it? Okay. Plus, now let's take a 64 out of that, and that's another 64, isn't it? 64 times 64t. Just kind of remembering that one. I believe that's right too, isn't it? 64 times 64. Or was that 32 times 32?
It's 32 times.
Okay, so it's 64 times 32, right? No, it's not. 16. 64 times 16. I knew that was looking like way too big of a number. Okay. 16t. So that's my numerator. Or better yet, factor it out. 64 times 16t 16t minus 25 root 2. Okay. Divided by 4 times the square root of 625 minus 200 root 2 t plus 64 t squared. Sometime I know that. Okay. I know 4 will go into 64 16 times. All right. Here's Dawson. Okay, top part of the alphabet doing quite nicely is that last part. And in fact, everybody in this class is in the top half of the alphabet, but that's just rather bizarre. Okay. Now, let's stop right there. That is our V dot A divided by magnitude of V. Because all we're doing is evaluating this when t is equal to 0, 1, and 25 root 2 over 16. So, if it's all right, I'm going to erase a bunch of stuff. Namely, these intermediate lines here. Now, it sounds easy to erase, but I don't, it's taking a while to do so. I'm hoping I'm not going to need anything else, but just in case I do. Okay. Now, so what I'm going to do is plug t equals 0 into that upper thing there. So, A sub t, tangential component, evaluated when t is equal to 0, is 16, and I'll just leave off the 0 part, times a minus 25 root 2 divided by the square root of 625, and the rest of it is zeros. Right? So that's way more than I need there. Okay, square root of 625, I think was, oh, wait a minute. This is such an aggravating thing. The screen just decides to go blank sometimes. 625 is a perfect square of 25. It's 25, yeah. So this will be 16 or minus 16 root 2, because the 25s will cancel out. Now, tangential, and that's what they have to, negative 16 root 2. okay? They approximate that to be negative 22.6, okay? Tangential component of this, the tangential component is the component in this direction, and for the acceleration, okay? The acceleration vector, remember it's a curve going up like this. The acceleration vector always points toward the inside of the curve, except you've got the tangential component of your acceleration. It is slowing down because this is pulling it down. So it kind of makes sense that tangential component would be negative, but just a little bit. It seems like to me it still should be a bit more positive than that. So let's do the same. This A sub t evaluated at 1. Okay? Don't need that mess in the way. So this is going to be, again, our 16 here times 16 minus 25 root 2 over the square root of, okay, that's a lot worse, the square root of 625 minus 200 root 2. I'm pretty sure that's a plus there at the end, isn't it? Yes, it is. Plus, it's just not showing up well here, okay? Plus 64. Okay. Now, they don't do any easy calculations here. They just do it. So I'm going to have to ask y'all to do the calculation. It's going to be another negative number, I can tell from that numerator. Okay, 16 times 16 was our 1024, I believe it was, minus 16 times 25 root 2. Just get your calculator out and do it. Say that again. 15.36. Is that what you said? They rounded it to 4, so I'll buy that. Okay. So the tangential component is getting a little less, okay? And then the last one is that fantastic number of t is equal to 25 root 2 over 16. And I do believe I'm going to have to erase some stuff, so let's do it. I'll erase this line down here. I've used it where I need it, so I don't think I need it anymore. I can't get it to erase though. And I happen to have erased my square root on the previous thing. I think I'll erase everything on the bottom part here too. Well, I'm through erasing, but it hasn't started doing all of it yet. Okay, let me get the last few marks that are in the way. Okay. I lost my square root sign here. Now, A sub t, unit tangent vector, at that wonderful number of 25 root 2 over 16 would be, let's just do the numerator to begin with. That was a 16 times, gotta wait till my pen catches up, and of course it's not going too fast, 16 times 25 root 2 over 16 minus 25 root 2. And that's why I'm going to stop right there. Because here, these 16s go out, and you got 25 root 2 minus 25 root 2, which is 0. And it doesn't matter what that denominator is. It doesn't matter about the 16 in front. That's going to be 0, and that's what they gave us. Okay? Now, the tangential component of your acceleration is finally going to come to a halt at that time. And now all your acceleration is going to be downhill. Which was, and I've already erased it, yeah, I knew I didn't do that. That was your negative 32, remember? Where do I have it written? Negative 32t. All of your acceleration is down. Nothing tangential there. So this is the point where your horizontal velocity stops. In other words, you've reached your peak. And then after that, your acceleration is all going to be downhill. Always was downhill, but now you've got a component back in this direction, that direction. Okay, so that's where that is 0. All right, so you can see from the figure here that the maximum height is where t is equal to 25 root 2 over 16, where the tangential component is 0. It's reasonable because the direction of motion is horizontal at that point. The tangential component of the acceleration is equal to the horizontal component of the acceleration. So, anyway, the wording is rather bizarre. So that finished 12.4. And I don't always say it, but the concept check is not a bad thing for you to think through, so always do that. I just start with the exercises. Any of the odds 3 through 7, all at Calc Chat, 5's at Calc View. 9 through 13, all at Calc Chat, 9's at Calc View. 15 to 19, all at Calc Chat, 15's at Calc View. 21 or 23, both at Calc Chat. 25 to 29, all at Calc Chat, 27's at Calc View. 31 or 33, both at Calc Chat. 35 to 39, all at Calc Chat, 35's at Calc View. 41 you can explore doing, that should be at Calc Chat as well. As would be 43. Then they start going into a little bit, well, 45 is cycloidal motion. Only problem they have like that, so that should be at Calc Chat. Then any of the odds 47 to 51, they should all be at Calc Chat. Any of the odds 53 or 55, they should both be at Calc Chat. Now this is an alternative formula for the principal unit normal vector. It doesn't look like it's that much easier to deal with than what the one we were using, but you can do it if you like. 57 and or 59, both projectile motion problems, they should be at Calc Chat. Well, actually, oh yeah. Then there's the air traffic control problem. 61 should be at Calc Chat. 63 should be at Calc Chat, centripetal acceleration. Either 65 or 68, orbital speed, should be at Calc Chat. And 69 is a true false, it should be at Calc Chat. 71, motion of a particle at Calc Chat. 73 and 75 are proofs, and they should be at Calc Chat. Any questions on those? And that, I think, is the end of 12.4. Finally, we'd already done this problem. All right. So let's move on to, if there are no questions, to 12.5. Last section in chapter 12, which means we'll get started in this today. And this is not a trivial section, either in length or in complexity. But hopefully we'll finish it today and Wednesday. And whether we finish it Wednesday or not, I'll try to have your test ready for you on Wednesday so you can be working on those. So you won't be mad at me this weekend that you have absolutely nothing to do. So you'll be able to do that. All right, so let's go from current slide. We're still in chapter 12, which is vector valued functions. This time we're looking at arc length and curvature. The objectives here, 4 of them on this slide, I think this is going to be it. Find the arc length of a space curve. Not a trivial matter, but it's not that far removed from what arc lengths were on plane curves, which I know you remember how to do those. We'll use that arc length parameter to describe a plane curve or a space curve, and the arc length parameter describes them very, very well. It's just really hard to calculate what an arc length parameter is. So even though it gives a great description, they're really hard to calculate. Then we'll find the curvature of a curve at a point on the curve. Okay? That's what curvature is all about. And we'll use the vector value function to find frictional force. Okay. So let's first look at arc length. The formula for arc length of a plane curve has a natural extension to any smooth curve in space. Now remember what we mean by smooth curve? Differentiable in every dimension. Okay? Needs to be that. You can't have any jags, cusps, corners, or discontinuities. It has to be a smooth curve in space. So here's the theorem that tells you exactly what that arc length is. If C is that smooth curve given by R of t is some x of ti plus y of tj plus z of tk on an interval, and this is the interval for t, your independent variable t, a to b on t. Then the arc length of C on that interval, and again, S is the symbol for arc length. Okay, we use that way back in trigonometry, if you remember. S is the symbol for arc length. So integral from A to B, those are the limits of your t here, of the square root of x prime squared plus y prime squared plus z prime squared. Okay? Another way of looking at that is the integral from A to B of your velocity, the magnitude of your velocity vector times dt. Okay? The integral of that with respect to time. Now, because remember, this thing squared is remove the square root and you've got exactly that. Okay. So, in many of our problems, we've already calculated this. It could be messy like we just had before, but that's exactly what you'd be integrating here. Okay. Not a trivial matter, by the way. So here's example 1, bottom of page 855. Find the arc length of the curve given by ti plus 4/3 t to the 3/2 j plus 1/2 t squared k. What a beautiful sounding curve that is. And we're going to do it from 0 to 2. Okay? Now, if you thought my drawing anything in 3 dimensions was sort of crappy, you should see it when it comes to curves in 3 dimensions, and you're cutting too much. Okay? This is coming out of the board at you here and curving around this way. So as far as I can tell, we're all in what I would call the first octant. That's a z being positive, x positive, and y positive. But I can't swear to that for sure. I believe it is the case, though, because I think all those things would be positive here. So you're in this first octant. Of course, they've twisted their axes around so it gives it the best light, but it's still not very clear. It's coming out of the page, coming up, and going like that. Okay? But we want the arc length of that. Now, what are we going to have to do to get that? What are good answers to most questions like that? Take a derivative. So let's get my pen set up. And your r prime of t is equal to what? Aye, that's yes in Navy speak. Not that hard, is it? 12 over 6, which is 2t to the 1/2 j, okay, plus tk. All right, there's your first derivative of this function. Okay. What do we do with that? Second, find its magnitude, which would be, let's see if we can do it here. What would that be? First term's not too bad. 1, all right, we got it, plus
4t to the 1/4.
Wait, well, you're squaring it, aren't you? You squared the 2 to get 4, square the t to the 1/2, and you get square. Okay, no, I'm sorry. Okay, I said it wrong. Well, you're not squaring the 1/2, you're squaring t to the 1/2. In other words, you're squaring the square root of t. T, okay, for 2, never mind. For 4, never mind, okay. Plus t squared. Now, I hope you realize, oh, maybe not. No, so close. No, I was going to say that we have a perfect square, but we don't. It's off, okay? Not quite have a perfect square, okay? Which is kind of a big boo hiss, okay? What we're going to do is take this square root and rewrite it as t squared plus 4t blank plus 1. I don't know if y'all were, no, some of you were not in my classes to know what a blank meant there. Does anyone recall? I'm going to do something you probably wish you would never have to do again, but yeah, you do. Complete the square. Okay, so we're going to put this by itself here and complete the square. What would that have to be? Plus, you said 2, or half of 4 is 2, but then you square it and that becomes a 4. But what have you just done? Added 4 here, so you better subtract 4 there. Okay, now we've completed the square, or almost. What would this be? The square root of? Second? T plus 2 squared minus 3. Yay or nay? Got it? See why we did it. Maybe not, but we did it anyway. Okay. Now, this, which is this thing, this is what we're needing to integrate to get your arc length. Remember? That's why we were doing it. Okay? And we're integrating from where to where? So S is equal to the integral from 0 to 2 of this thing. The square root of t squared plus 2, t plus 2 squared. I feel like my 112 students, they just throw those squares in anywhere they want to, okay? Squared minus 3 dt. Okay. Why not put it inside the parentheses? It's just as good there as outside. It's cozier in there, you know. I just graded a bunch of tests. It was sad. Okay. Now, how do we do an integral like that? Does anyone remember a technique?
Well, I believe we would throw 2 in there first.
What's that?
I believe we would throw 2 in there first.
Throw a 2 in there first.
Told you you substitute.
Okay, what substitution? Is that what you said?
He said you substitution.
Which?
He said you substitution.
Okay, what substitution would you use?
2 plus 2.
Say again?
2 plus 2.
Okay. Let u equal that? Is that what you're suggesting?
Yes.
Let's try it. Let u equal t plus 2. Okay, then du is equal to dt, right? And that would give us s is equal to the integral. Now, since you're changing from t's to u's, let's change our limits on our integration as well. It would be from 2 to 4. You're absolutely right. Of the square root of u squared minus 3 dt. That's much better, isn't it? Oh, I'm sorry, du.
Why would you try to do 2 to 4? 4 to 2?
Well, because these are the limits on t. When t is 0, u is 0 plus 2 is 4. And we're doing du's down here. And when t is 2, 2 plus 2 is 4, so that's your 4. See? Got it? Now, is that a whole lot better?
What, can you explain that again?
Okay.
Explain that same thing.
All right. You're going from, these are your limits on t. T going from 0 to 2 here. You're changing your variable from t to u. So you change your limits for that. So when t is equal to 0, add 2 to it, and your u will be 2. When t is equal to 2, add 2 to it, and your u will be 4. So these are those limits for u that corresponded to those limits for t. Okay, and this is your integral now. And what do we do with that?
I guess we would integrate.
What's that?
I guess we would integrate.
I can hear you. Okay. Now, square roots of squares sort of should help something come to mind. Say again?
Trig substitution?
A trig substitution, fantastic. What trig substitution would you like to use? Which one is a something minus the number rather than the minus square root of? Oh, it's about to explode. Okay, no, okay. Critical mass. No, well, cosine would be if it was 3 minus u squared. Sine would be the same thing. Tangent would be without the rounding. All right. One more guess. One without a co in it. The only one you haven't said. Secant. All right, let's try a secant. Okay. So let's let, this time we do it a little differently. Not that we let u equal something in t, we let, well, it's a u, it's u equals something in theta. Okay. Now we got another problem here too, and that's the square root of 3. I mean, that's the 3 here, and that's supposed to be a sort of a perfect square too. So let's do the square root of 3 times the secant of, and what would be a good angle variable to use? Theta, did I hear? That sounds like a great idea. Okay? Now, we're going to do several things with this. The first thing we're going to do is square it, just like we have there. So then u squared is equal to what? 3 secant squared. Theta. Okay? Now, let's subtract the 3 from that. And you have 3 times secant squared theta minus 1. And what is that? The whole reason we went to this, that is a tangent squared. This would be 3 tangent squared theta. Okay, that's about as far as we can take that branch of the problem. We also need a du down here. And what is the, I'll do the square root of 3 part. You tell me what the derivative of secant is. Oh, explosions again, huh?
Is it secant times tangent?
You got it. All right. Secant theta times tangent theta. All right. Then with a d theta in it, right? We got to have our d's with our d's. Okay. Now, I sure don't want to change my limits on this one. Huh? Okay.
Is that d theta?
Yes, it is. Yeah, whenever you do the d's, you have a d. This d always has a d with it. And look at that, perfect attendance today. All right. Way to go, team. All right. Now, if it's okay with you, I'm really inclined not to change my limits on the 2 and the 4, if that's all right. It may be doable, but it's sure not easily doable, I don't think. Okay? You would have to have what? Well, let's just leave them alone for now, carry them through, and we'll come back with our u's when we get ready for u's and plug those back in. All right, so let's see what we've got. S is equal to, I'm going to do the integral sign without limits, okay? Now, we have here, we didn't do this. We could do one more step here, and that's the square root, because we had the square root of u squared minus 3. This is u squared minus 3. The square root of that is going to be root 3 tangent theta, right? The square root of this stuff is going to be the square root of that, which is root 3 times tangent theta. So, there was a question? No, okay. So the argument here is root 3 tan theta. I'm going to put the root 3 out front for now, if that's okay. Tangent theta. Okay?
Still square root, right?
No. You see, I took the square root of u squared minus 3 here and there, and that left me a root 3 tangent theta, because the tangent squared theta was there.
So tangent theta is not in the square root?
No. It was the square root of 3 tangent squared. When I took the square root of 3 came out, and the square root of tangent squared is tangent. Okay? So, I pulled the root 3 on the outside. Now, my d theta is another root 3, so that makes that's a 3 outside. And we have a secant theta here. And then another tangent theta will make that a tangent squared theta, d theta. All right with that? That's a 3. There was a square root of 3 from this part, and there's also a square root of 3 from your du part. Remember yeah. Okay. And square root of 3 times square root of 3 is 3.
Not to mention there's other tangents around.
What's that again?
Not to mention there was another tangent.
Yeah, and that's why it's a tangent squared. You have a tangent from here, a tangent from here, that gives you a tangent squared, and a secant from here, secant, and then a d theta from here, d theta. So that's our integral. Now, how do we integrate that?
You have to integrate again.
Well, yeah, we still haven't integrated it. We've just been manipulating it.
Do we still have 2 and 4 there? Or?
No, well, I left those off. I'll bring those back when we change back to use. Okay?
Can you split that up, maybe?
Question.
Oh, let's see. How do you mean?
Like, do integration by parts?
Well, you might be able to. Let's think about this for a moment. Derivative of tangent is secant squared, unfortunately. Derivative of secant, though, is secant tangent. So neither of those look like they're very promising, do they? Have I botched something up here? I may have taken us down a wrong pathway. Sorry about this.
No, you got to finish it.
Nah, this is going nowhere fast. Oh! You know what they did? Clever. They went to the integration tables. They didn't do any of what we were suggesting. They went straight to a integration table. And I would suggest they're going straight with this. They didn't say that, but that's, so sorry about, but that was a good review, wasn't it?
Yes.
It just didn't work out for us, which is how math goes a lot of time. Okay. I think here on down. It was heading in a promising direction, but just started falling apart toward the end. Okay. So we're going to an integration table. Back of the book, before the index. I think I've got it marked back here. No, I don't. I did. Okay. Is it before the answers? I don't think so. I think it's before the answers, not after the answers. Yeah. I don't know. Oh, I do have it marked. Here's our integration table. These are forms involving radical a plus bu. We got a squared. Here we go. If you look at the ones back on page Appendix B, A4, no, page A4 of Appendix B, from 26 to 35 are forms similar to what we have here. And I think it's that very first one, 26 there. Okay? U squared minus a squared. So our a squared is the square root of 3 squared, not cubed. Okay? That's our a, square root of 3. Okay? So let's see what we got. And this is a minus sign there. And this will be, I'll do it over here, following their lead, 1/2 times u. Well, that's u, okay? All right, times the square root of exactly what's under here. So rather than writing it, I'm just going to do u squared minus 3, okay? And then it's because we have a minus, it's going to be a minus 3. That's your a squared, it's 3. I got lost. There it is. Times the log, yuck, natural log of absolute value, your u is u, plus that very radical you got, square root of u squared minus 3, close parenthesis, close absolute value, and then they have a plus c. Okay? And this will be evaluated from 2 to 4. Okay, that's our u's. So let's go up to the top and do this. Your S is equal to 1/2, okay, and u, when u is 4, this would be 4 times the square root of 4 squared is 16 minus 3, 13, minus 3 times the log, natural log of absolute value, 4 plus, that was a plus, wasn't it? Were y'all following me?
Yeah.
It wasn't a minus. Okay. Somehow in my head I thought,
It was u plus root u squared minus 3.
okay. Oh yeah, it was a plus. It wasn't a plus or minus. Okay. The A was the one that was the minus 3. Yeah, got it. Okay. I think I forgot to do that, didn't I? No, it's there. Minus 3 times u plus, and this was the square root of 13 again. And that was a plus there too, wasn't it? Or was that? I'm doubting myself too much. Yep, that's a plus there too. Yeah, okay. Okay. All right. That's with the 4 plugged in there. Minus, and the 1/2 is in front of all this, 2 times the square root of 4 minus 3, which is 1, right? So I'm not going to write square root of 1 anymore. Minus 3 times the log of absolute value 2 plus 1. Okay? All right. So let's see what we've got. 1/2 times 4 root 13 minus 3 times the log of, and that's going to be positive, so I'm going to drop the absolute value bars, 4 plus root 13, minus 2 minus 3 log, log 3. Okay. What a lovely answer. Is there anything we can do to simplify? Frankly, I don't see. Do they have any way of simplifying? They have 2 root. Oh yeah, well, okay. I'm running out of room very rapidly here. I think I'll go and erase this thing here. I've already used it. And I think I used it correctly, so we'll get rid of this, and we'll simplify as much as we can. All right. 1/2 of 4 would be, your arc length would be 2 root 13 minus 3/2 the log of 4 plus root 13 minus 1 minus 3/2 the log of 3. Okay, I don't need that anymore. All right, let's see how close we are now. 2 root 13 minus 3 halves log of 4 plus root 13 minus 1. Whoops. That's a plus, and somewhere I've erased, yeah. Yeah, when you did the bottom, that should have changed that to a plus. So sorry about that. I forgot. Ooh, like I've told you before, minus signs are there for one purpose only, and that's to trip you up. So that's a plus 3 halves log 3. Yeah, because I changed the sign of the first part, I forgot to change the sign of the second part. Okay. Yep, that's the answer they got. Now, if you have a calculator and want to plug that number in, see what you get. They say it's about 4.816. And what does that mean? Oh, that's the arc length. That's how long it is from t equals 0, which is right there, until you get there. And just looking at this, that seems to be fairly reasonable, because it seems to be fairly close to the y-axis, not exact, and it's going, out a certain ways on the y-axis, but then the extra curvature and the rise that you have, if you straighten that out, it does appear to be something you could easily imagine something greater than 4. Kind of. Okay. Does that make sense? Arc length's fun. Okay. Let's see how they did it. I think it's going to be pretty similar. Using x of t as t, y of t as 4/3, t to the 3 halves, z of t is 1/2 t squared. You obtain x prime of t of 1, y prime of t is 2, t to the 1/2, and z prime of t is just t. So your arc length from 0 to 2 would be the square root of the first one squared plus the second squared plus the third one squared, square root of all that, dt, which would be the integral from 0 to 2 of 1 plus 4t plus t squared dt. And then by completing the square, they flipped it around, completed the square, and got t plus 2 squared minus 3. Now they went straight to the table from there, and instead of going to u, they used the t plus 2. And if y'all wanted to do the t, I wanted you to go that way because it's easier to see in the table, and usually easier to mess with. But you see, you get the same thing. Everywhere you have a t plus 2, that was a 4. Everywhere you had a t plus 0, that was a 2. So we did the same evaluation here. We just used u rather than t. And that's what they got. And they came out with exactly the same answer and approximated that to be about 4.8. Okay. Now, this handy-dandy little arc length parameter. But before we go there, they're skipping example 2, which somehow doesn't seem like too bad of an idea. But let's go on and do example 2. Find the length of one turn of the helix given by r of t is equal to b cosine t I plus b sine t j plus the square root of 1 minus b squared what a nice coefficient t k. Be sure you close out that radical there before you get to the t, and make sure you remember the t's in there. Okay. Now what are we going to do with that? And when it says the length of one term of the helix, that's from t going to from 0 to 2 pi. Now, of course, it's not going to be closed because that k is taking us upward as we go. So, but just one time around from 0 to 2 pi. That's what it means one term. So why didn't they just say 0 less than or equal to t is less than or equal to 2 pi? Don't know why they are just say 0 to 2 pi for our limits on t. Okay, that's the interval. Okay. How would we begin? Take a derivative, I hope is what you mumbled. Okay. And what would that be? Got it? Got it? Square root of 1 minus b squared. That's just a constant. Take the derivative of that, and that would be your k. And what do we do with that? Magnitude of that. I'm just going to call it r prime. This will be the square root of. Okay, wait. Remember what you're doing? Squaring the derivative, right? The terms. So that would be b squared. Continue. Sine squared t plus the sum of these squares, of each of these factors squared. See, whatever the x prime was squared plus whatever the y prime was squared plus whatever z prime, all under the derivative. Okay, kind of like your distance formula, which is exactly what it is. Okay. So what's the next one? B squared cosine squared t plus plus 1 minus b squared, because you're squaring a square root. And there's no t's in that one. All right. Let's simplify that a little bit. What can we take out of the first two terms? A b squared, and that leaves us sine squared t plus, that's a t, plus cosine, and that will be 1, okay? So that's equal to 1. So you got a b squared plus a 1 minus b squared. And what will that give us? 1, all right, okay, wow. And the square root of 1 is 1. And what do we do with that? Integrate it from what? 0 to 2 pi dt. And that would be 2 pi. Ooh, that sounds good. Now I'm hungry. No. Okay. Sure enough, 2 pi. Not too bad, huh? A lot better than the last one. Okay? A whole lot better than the last one. Okay. The length of that one time around, and frankly, they're, oh, I see. Yeah. They're coming all the way around. It faded out back there. I thought they were stopping somewhere back there in that third octave back there, but they came on around to the first octave. Well, at first, to the x-axis again. All right. Now we move on to, any questions on that before I go on to arc length parameter? All right, the arc length parameter. We've already been talking about it, sort of ad nauseum. Here's what it is, the definition of the arc length function. Let C be the smooth curve, as we've had before, given by R of t defined on some closed interval t going from A to B, closed interval A to B, and for t somewhere in that interval, the arc length function is now not just an arc length, it's an arc length function of t is the integral from A not to B, but from A to t times the magnitude of that r prime of u du. Now you see, before we had t's in here, but when you make that your variable up here, you need a dummy down here. And you are as good a dummy. No, I didn't say that, did I? Okay. But you need another variable down there. And they chose you. Why? I don't know. But anyway, this will be the integral of, and now everywhere you had a t before, you just put in a u instead. Okay. Now that arc length s is called the arc length parameter. Okay. It's now a function of this t. Okay. So in other words, before we were doing the length from t equal a to t equal b. Now we're using the s of t is the length from t equal a to anywhere along the curve up until you get to b. And that would be some function of t. If t's down here, it's going to be a little short thing. There, it's going to be pretty moderate. There, a little bit longer until you get to the end, which is what we were doing before, integrating all the way to b. So this gives us s, the arc length, as a function of t, as long as t is between a and b. Now, why would you want to do that? Okay. I didn't want to. No. All right. Using the definition of the arc length function, or s is a function of t now, and the second fundamental theorem of calculus, you can conclude that this ds dt, the time rate of change of that length that you're going along there, is your speed. And that's exactly what it should be, isn't it? Because the arc length is how far you're moving, and this is a rate. The change of distance per change of time is the speed. Not velocity, but speed. R prime, without the absolute value, would be velocity. That's all sorts of changes because it's got directions involved with it. This is just the speed. That's the derivative of the arc length function. It's just your speed at any time t. In differential form, you could write that as ds is equal to r prime dt. Looks like you just multiply both sides of the equation by dt, but of course you didn't do that. You just wrote it in differential form, which is doing that. Okay? So, got it? Example 3 then is taking this, find the arc length function s of t for the line segment. Oh, this is going to be fun, isn't it? Given by r of t is equal to 3 minus 3ti plus 4tj when t is going from 0 to 1. Okay? Now, how do we know that's a line segment? If you adjusting this, they hadn't told you that before, would you know that's a line segment?
Yes, because it's only got I and j.
Everything's to the first power of t. A constant or first power of t. Okay, so that is a line segment. And we want the arc length function, s of t, of this thing. So what's the first thing we're going to do? Oh, y'all have answered it well so far. Take a derivative. R prime of t is going to be what? Yep. Huh? Second, negative 3i plus 4j. Perfect. Okay? Now, what do we do with that?
Now you take the magnitude.
Second?
You do that, find the magnitude.
Okay. What's the magnitude of this? Okay.
The root of 9 plus 16, which is 25. So
5. Good. 3, 4, 5 triangle. Okay. There's your R prime as a function of time too, by the way, because we differentiated those out. Okay, but we want the S of t. What was the S of t again? Yeah, it's the S of t is equal to the integral from your lower limit, 0, not to 1, to t. And then you do this magnitude, which is just 5 du. Can't use t there anymore. It has to be a u. Okay? Now this is almost coming out so stupidly simple, you think, are we doing this right? But indeed we are. What does this come up being? S of t is equal to 5t. Okay. It's speed times the time that you're going at that speed, okay? Because it's a constant speed, okay? And this is good from t is equal to 0 to t. So there's your S of t. It's 5t. And write r as a function of the parameter s. R is a function of this parameter s. Okay. Well, we've got r as a function of t here, don't we? Please say yes. So this is right. So let's get over here t is a function of s. So wouldn't that be dividing both sides by 5? So you get t is s over 5. Right? Okay. So we come up here and do your r of t as a function of s. Okay. I want to write s over 5 there, but let's just have r. So this would be 3 minus, and your t is s over, 3 times s over 5, so 3/5 s. Yeah. I plus 4 times 4 over 5 s j. I think this will just be t as a function of s. You don't have to write the other. So that's 3 minus 3s. Let me write it a little neater. 3 minus 3/5 s. That's not a 5. I plus 4/5 s j. Okay. All right. And if you'll see just before that red block that you see almost at the middle of page 857, r of s is equal to 3 minus 3/5 s I plus 4/5 s j. We said it left a little more room and not made the s's quite so small. See, the numbers are so much bigger than the variable. It makes it look like the variable is a subscript or superscript or something. It's not. It should be the same size. Okay. All right. Now that's for a straight line, which is a linear function, which shouldn't come as too big a surprise. All right. Let's see how they did it. I think it was fairly close to the same way we did. R prime would be minus 3i plus 4j. R prime t would be just like you did. Magnitude of that would be 5. And your s of t would be the integral from 0 to t of 5, okay, du. I put the 5 on the outside, they left on the inside. Doesn't matter. and this would be 5t. Wherever you put it, it comes out 5t. Now, using s equal 5t, you can then rearrange that to be t is equal to s over 5, then go back to your r of t function, but put it r of s now, but everywhere you had a t, put s over 5. So that gives you 3 minus 3/5 s I plus 4/5 s j. Okay, they got the s's a little bit bigger on that one, or maybe they put the number smaller. I don't know, but it's a little easier to read. And now the s is going from 0 to 5, not 0 to 1. T was going 0 to 1, but you see, as t goes 0 to 1, here, the t, 0 to 1, the s is, t equals 0 gives you 0, t equals 1 gives you 5. The s is going 0 to 5. All right. Now, they left out some verbiage here that I want to go on and sort of read or say. I don't know how many of you have books or don't have books. One of the advantages of writing a vector value function in terms of the arc length parameter is that the magnitude of your r prime square, r prime of s is always 1. The speed with respect to s, not with respect to t, but with respect to s, well, you can't even call it speed anymore. Your first derivative of that as a function of s is always, 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 always 1. And in that last example, I was trying to find where, oops. Yeah, okay, I can go back to here. All right, down here. If you take the first derivative of this with respect to, as a function of s, you get minus 3/5 I plus 4/5 j, right? And take the square root, take the absolute magnitude of that, the square root of 9/25 plus 16/25, 25/25, which is 1. Your magnitude of r of s is always going to be 1. Okay. So for a smooth curve represented by r of s, where s is the arc length parameter, the arc length between a and b is merely b minus a. Okay? Just the difference of those, the length of the interval. Furthermore, if t is any parameter such that the magnitude of r prime of t is equal to 1, then t must be the arc length parameter. So those two added together give you this theorem. Well, and other stuff we had earlier. If c is a smooth curve, given by not r as a function of t, but r as a function of s, where s is the arc length parameter, you have s of x I plus y of s j on a plane curve, where r of s is equal to x of x of s I plus y of s j plus c of s k in a space curve. Either one, as long as that c is a smooth curve in every dimension, where s is the arc length parameter, then the magnitude of this r prime of s always has to be 1. And then they say the same thing again. Moreover, if t is any parameter of a vector value function r such that r prime of t, magnitude of that is 1, then t must be the arc length parameter s. If you ever had those, nice. You don't have to go back and get it. But if you don't, well, arc length parameters that make for nice formulas, they sometimes are real bare to compute. So let's move on to curvature. Important use of arc length parameter is to find the curvature. That's the measure of how sharply a curve bends. Okay? Here in this curve, it's bending really sharply here. So this would have a large curvature at P. But up here, it's bending really, really, really slowly. So that's going to have a very small curvature there. Okay? Is a measure of how sharply the curve bends. For instance, in this figure, the curve bends more sharply at P than Q, so you can say that the curvature is greater at P than it is at Q. And again, this is a smooth, this happens to be a plane curve. That would work if this was a spatial curve as well. Okay? It's sometimes hard to see whether it's bending sharply or not so sharply on a spatial curve, because some of it could be coming at you. You can calculate curvature by calculating the magnitude of the rate of change of that unit tangent vector. That tells you how fast it's turning. Because if this unit tangent vector is here at T1, then it's T2, then it's T3. All these are unit lengths. But you see, the rate of change of that is quite dramatically large. Whereas if you did the same thing here, this T right here would be here, the T right here would be there, the T right there would be there. Very little change in those. So the rate of the change of your unit tangent vector is also a measure of that curvature. Okay? Rate of change of the unit tangent vector with respect to that arc length S. So you see all these arc lengths are identical. You know, this is the same arc length here as that arc length there. So your change of T with respect to equal S's is fairly dramatic. Okay? Whereas if you did the same arc lengths here and did your T here, T there, and T there, hardly any change at all. Very small curvature. So the magnitude of the rate of change of T with respect to the arc length is the curvature of the curve. So here's your definition. If C is a smooth curve, it's either in the plane or in space. All things have nice predictable derivatives. Given by R of S, now you've written an arc length parameter as your parameter. S is the arc length parameter. The curve K is given by simply the magnitude of dt ds. Okay? The T is your unit tangent vector. Other way to write this is magnitude of T prime as a function of S. Now, a circle has the same curvature everywhere, okay? Because it's changing at the same rate everywhere. That's what makes it a circle. Moreover, the curvature and the radius of that circle are inversely related to each other. Now think of this. So it's a really small circle, that unit tangent vector is changing really quickly. So a huge circle, that unit tangent vector per arc length, is going really slowly. So those are inversely related to each other. Okay? That is, a circle with a large radius has a small curvature, a circle with a small radius has a large curvature. And the curvature is always the same throughout that circle, just different for different sized circles. Okay. So here's example 4. 2 minutes?
No.
3 minutes?
2 minutes.
2 minutes.
1 minute.
Keep talking. 1 minute. Okay, now. Okay, right. 30 seconds. Okay. Okay, why don't we end? Okay. I think that would be just about the time for me to give you homework exercises, wouldn't it? So we'll pick up next time with example 4 on page 858. And it looks like somewhere here I must have had a mark before, but I don't see it. I'll just erase this one a little bit better than what it was erased before. Okay. Okay. Stickies in there for some reason. Okay, 12.5 homework exercises. Do any of the odds, 3 through 7, they're all at Calc Chat. Do number 9, it should be at Calc Chat. Do any of the odds 11 through 15, they should be at Calc Chat. 13, is at Calc View. And you might try looking at 17. It should be at Calc Chat as well. And we'll pick up and do curvature next time. And I'll also try to have your tests ready for you next time. I think I will, if I can just remember to have them run off in time. It's my first class, so I've got a bit more to do to get those ready. Good deal. Any questions? We will catch you, 2 of you tomorrow and the others on Wednesday. All of you on Wednesday.